Now we come to the session 5. So students are familiar about subring subfields, similar to simple theorem on subring forms. So we come to the ideals. What is an ideal? Suppose if we take an integer, suppose if we take an set of all integer, minus 3, minus 2, minus 1, 0, 1, 2, 3, etc. So this element I am multiplying any other element belongs to R in elements R. So either left side, either right side. You are multiplying the left side is called left ideals. If you multiply the other side is called a right ideals. Ideals is a non-empty subset of R. Is a non-empty subset of R. Is said to be a left ideal. First, ideal must be a subroof of R. Ideal is a subroof of R with respect to additions. Then R into S belong to S. For R belong to R, S belong to S. Yeah, R is an element of a ring R. S is an element of S, a subset. When this element you are multiplying the left hand side in the subset, the element belongs to R, multiplying the left hand side, the subset, we get a left ideal. It's called a left ideal. Again, we come to the non-empty subset S of a ring R is said to be a right ideals of R. Again, S must be a subroof of R under additions. Then S into R belongs to S. S into R belongs to S. Then R is an element of R. You are multiplying an element R in the right hand side. It's called left ideals. It's called a left ideal. See, if we come to the extend its elements, a non-empty subset S of a ring is said to be an ideal if and only if it is both left ideal or right ideal. Whatever may be ideal, simply say an ideal. If either multiplying the left hand side or right hand side, simply say is an ideal. See, thus a non-empty subset S of a ring is said to be an ideal of R if S is a subroof of R under additions. S is a subroof of under additions, additive group. RS belong to S. R is an element of R. S is an element of S. R belong to element of S. S belong to element of S. This is an ideal definitions. So whatever may be either right or left ideal, simply say an ideal. Ideal is a subset of R. Subroof of R under additions. Subroof of R under additions. If you take an elements in R, you take elements in R, you are multiplying either right or left side. That is called is an ideal form. Is ideal. See here and 0 and itself simply proper ideal. Improper ideal. Other ideal is called a proper ideal. So suppose if you take generally if you take S is an ideal of a ring R, then S is also a ring of R. You know the previous definitions. What's the ring property? A is there, B is there. A is there, minus B is there. A plus of minus B equal to A minus B belong to S. A is there, B is there, A B is there. The same property hold that, but every ideal is a subring. Subring may not be an ideal. Given a next example, next session examples. If an S is an ideal of a ring R, then S is also subring of R. The obvious reason is that S is a subroof of R under additions. Form a conditional to multiply conditional. For we have X into S belong to S. Here X is an element of a ring R. X is an element of a ring or S is an element of S. Then X also an element of S. That is also an element of that implies X belongs to R. Thus S is closed with respect to multiplications. S is closed with respect to multiplication. Yeah. Therefore S is a subring of R. Thus every ideal of a ring R is also subring of R. Every ideal of R is also subring of R. Keep it in mind. Every ideal. What is ideal property? Subring property is also same, but ideal is stronger than a subring form. Subring, right. Multiplication is stronger. I give examples Next slide, observe. But every subring is not an ideal. Every subring is not an ideal. An ideal required a stronger closure property than the subring. Ideal required a stronger closure property than the subring. If S is a subgroup of R under addition, then S will be a subring of S is closed with respect to multiplication. That is, product of any two element of S again in S, but S will be an ideal if the product of any element of S with any element of R is in S. You observe that? We are observe this. S will be a subring of S is closed with respect to multiplication. The product of two element of S is again in S, but S will be an ideal if the product of any element of S with any element of R is in S. R ಅಲ್ಲಿ multiply ಮಾಡಿದ್ರೆ product ಮಾಡಿದ್ರೆ S ಅಲ್ಲೇ ಇರುತ್ತೆ, ಅದು subgroup ಅಲ್ಲೇ ಇದೆ. But that this I give an examples that if R is a commutative ring, then every left ideal will be also a right ideal. Therefore, commutative ring, every left ideal is also an ideal. So, this is a definitions regarding that every ring are always possesses two improper ideal. A ring always possesses means 0 is there, itself is there. This is called improper ideal. 0 and itself is a improper or trivial ideals. All other ideals, if you apply this, what are conditions other apply, this is called a proper ideal or the ideal. These are the respectively known as the unit ideal and the null ideal. Any other ideal of R is called proper ideal. A ring having no proper ideal, this simply called that simple ring. Simply called is a simple ring. Here, see, in this case, in the ideals, in his ideal, if we take a Z, Z is a ring of R. Z is a ring. See, a ring. See, ideal, what's the ideal? So, subring form, A is there, B is there. A minus B in A minus B in ideals. A is there, B is there, A B in I. Okay, this property is solved. What in case here, if A is there, itself is there. Suppose if you take an element in Z, Z is R. Multiplying any side of that, any side by the right hand side or left hand side, distributed either right hand side or left hand side. If we multiply this, for example, see, Z is set of all minus 3, minus 2, minus 1, 0, 1, 2, 3, etc. So 3Z is minus 9, minus 6, minus 3, 0, 3, 6, 9. See, so our concentration observe 3Z is an ideal. 3Z is an ideal. So what's in the 3Z? Minus 9 is there, minus 6 is there, minus 3 is there, 0, 3, 6, 9 is there. Suppose if you take an element in Z, Z is R is Z. Take element. Suppose if you take 2 in Z, 2. Suppose you multiplying that 2. So minus 18, minus 12, minus 6, 0, 6, 12, 18. Is again in I. Minus 18, minus 12, minus 6, 0, 6, 12, 18. Is an again ideal. So this is called an ideal. So here you are multiplying 2 in the left or right hand side, whatever may be. Again in 3Z, minus 18, minus 12, minus 6, 0, 6, 12 again. This again an ideal. This is the now next we go for next step. We give the examples regarding the right ideal.